Okay. So today we're going to be able to identify the domain and range, determine whether it is a function, and whether a graph represents a function. We've, again, at different points maybe been introduced to some of these things. Everything we've seen up to now is what's called a relation. And all a relation is a set of points, a set of ordered pairs. But those ordered pairs really have no rhyme or reason to them. There is no rules that govern a relation. When we look at that, the set of the first things in there, which would be 0, 10, 20, 30, 42 in this example, are called your domain. Typically, when we talk about a ordered pair, we would call that our x values, our input, or the independent variable, all of those different things. And this is a set, so these are just individual numbers. If I'm talking about a set of individual numbers, you'll see I use these curly brackets. Okay, in a little bit we're going to talk about interval notation, where it's like a whole bunch of numbers. This is just individual numbers, so I would list the first number in each of those ordered pairs as my domain. When you are doing this, I tend to do them in numeric order. However, it does not matter at all. Just get them all in there, okay? And then our range of a relation is the second entry in each of those ordered pairs, or the y value, or the output. All of those different ways that they are described. I'm just going to list them in the order they are up there. We will work with a relation every now and then, but most specifically, we are going to move on to what's called a function. A function is a smaller subcategory of a relation. Sure looks a lot like what's up here, but it's got some rules to it. All right, anyone still want this page up here? Okay, so now specifically we're moving on to what we will work most often with, and that is what's called a function. A function is a relation, which means it's a set of ordered pairs, okay? But specifically, each member in the domain, so each first number in those ordered pairs, corresponds to only one other number. Now, there is a whole bunch of different ways that we look at a relation to identify whether it is a function. One of those is this pictorial representation, where they put this circle of the domain right here and the range here, and we can see that each domain number, so 1 only goes to one number in the range, 2 only goes to one number in the range, 3 only goes to one number in the range. You can look at it like that. That could also have been, you know how we were making those tables of points? You could see that exact same thing in a table of points. It's just kind of another way of showing a table of points would be like this. And you notice that we don't have any repeats here. Or I could look at it this way, and again, what I'm looking for is repeats. The key to a function is the first value, the domain. Cannot have repeats in the domain to something other than the same number. Not a function, this is your key, going to two different numbers. One domain value that goes to two different range values. 4, 1 and 4, 2 are in that relation, which makes it not a function. This one is not a function because 2, 5, 2, 7. If they have the same x value, show up more than one, so to a different y value, it would not be a function. We could again represent that if we saw this one like maybe in a table or something. You would notice again a duplicate. It's all about the x values. Duplicate x value, 4, 1 and 4, 2. That makes it not a function. The 5, 3 is also in there, but that's not why it wasn't a function. All right. Sometimes we're going to be asked if it's a function or not a function by just looking at the equation. And in my opinion, the equation version is going to be by far the hardest way to identify if it is a function or not a function. But I will give you a little hint on what to look for. It is not the end-all be-all of the function, not function, but for our purposes, typically what you are looking for to decide if something is a function or not a function is if you were to have a y raised to an even exponent. If you have a y raised to an even exponent here, right? It's because if we were to follow these directions down here that say to decide, solve for y, and if 2 or more y values can be obtained for a given x, the equation is not a function. Yeah, great. I wrote that up there for you, but I don't think it explains what we're seeing here. Why does the y raised to an even exponent make this, 2 y values obtained from the given x, happen? Well, when I am solving, let's take this one for example. If I were to solve that for y, I would subtract the x squared over, right? And here's what happens. This is the even exponent part of it. To solve this for y, I would square root. Yes, that seems normal, yes. But when I square root, what's that thing that we're always supposed to put on our answer that we forget? Plus or minus, right? So I square root. Because I'm square rooting, I am supposed to put a plus or minus on my answer. And so what happens is I plug in an x. I plug in 3. I put it in here. That was a bad example because that's, how about I plug in 1. Okay, I put it in here. I get an answer, but it's both the positive version of that and the negative version of it, which means I just got 2 answers by plugging in one number. When I plug in 1 to this particular equation, if I show you here, if I plug in 1, I get 4 minus 1, which is 3, so I'd get the positive square root of 3, but I also get the negative square root of 3, and notice I got 2 answers for the same x value. That's not a function. And so it's that even exponent because when we get rid of the even exponent in our solving process, we have to put that plus or minus on there. Anything else, including a cube, would be a function. So for our purposes, that's what we're looking for, even exponents in equation format. Questions on that? Hard to see because there's not a lot else I can tell you. I can't tell you to graph it because your calculator needs it in this format and you would have to know to put in both of those to see that it's not a function. So raised to an even exponent. Vertical line test. This is what we use for a visual if we have a graph to look at and we're asked to decide if it is a function. So given a relation, deciding if it is a function or not a function, we would run this vertical line through it. If our vertical line will only ever hit our graph at one place, it's a function. But if that vertical line would hit our graph at more than one place, 1, 2 places here, not a function. That's 2 ordered pairs with the same x value. So now we've seen looking at the ordered pairs, deciding if it's a function, looking at the equation, deciding if it's a function, looking at the graph, deciding if it's a function. So let's go ahead and try that out. I want you to look through these three equations and decide on each one if you would decide that it is a function or not a function. Okay, I kind of tried to trick you on the first one. What do you think? First one, function or not a function? It's a function. You see that square root on there and it kind of made you hesitate, I hope. But it is specifically the negative version of that. It does not have a plus or minus. We didn't do the solving to get that, right? So it is just what it is. That actually is a function. Its graph would look something like, let's see, x plus 7, something like this. It would pass that vertical line test, right? So next one, function or not a function? Function. That one is a function, okay? We would only get, I would solve that. Which, again, we don't know how to draw that yet, but that one would end up looking something like this. That's a function. That right there, let's talk about that real quick with our vertical line test. Doesn't it kind of look like it might fail the vertical line test? But it continues to get closer and closer. So it's actually continuing to move to the right forever, very, very slowly. But it is slightly moving to the right. So if I drew a vertical line through it, it actually would still only hit it at one place. Okay, so when you see those that are approaching an asymptote, it actually does still pass the vertical line test. Function or not a function? Not a function. All right. Vertical line test, function or not a function? Okay, first one, does it pass the vertical line test? Yep, that's a function. Second one, does that pass the vertical line test? Nope. Okay, next we're going to talk about the topic of interval notation. And I do want to address a little bit, interval notation is what we will use in this class, like on the daily for the rest of the semester. And by that I mean year. We will continue to use interval notation all year, okay? It looks like an ordered pair, which can really mess with you at times because it is two numbers separated by a comma. Sometimes it also has parentheses around it. But it's indicating, and I'm going to show you this in a couple different ways, it's indicating a set of numbers. All of the numbers between whatever the smallest number is and the biggest number. Now you see that I have two marks on either end, a parentheses or a bracket. It will be one or the other, not both. They do have meaning. The parentheses means that that number is not actually included in the set. That's where you're going to start. But if I were to look at it visually, it'd be an open dot. The bracket says, yes, we include that number. Visually, it would look like a filled in dot. If I were to give you an example of interval notation, I'm going to give you a couple here. First of all, your two symbols do not have to match. What does that interval mean? It means that it is the set of all numbers that start at -3 and go up to 2. -3 is included in this set, but 2 is not. Now, here are some other ways that you have seen it showing that information. You have seen it as a compound inequality, an AND inequality. -3 is less than or equal to x is less than 2. Notice the connection between including with an or equal to. Not including is just a less than or greater than. No or equaling, we are not equaling to. You have seen it on a number line probably as a shaded area with dots. We are including the 3. That would look like a filled in dot. We are not including the 2. That would look like an open dot, and I would indicate that it is all numbers between there. So hopefully kind of tying that to some things that you have seen before for our interval notation. Now, going back to the domain we saw at the beginning, I could not have described the domain that way because it wasn't all of the numbers between where we started and where we ended. It was just select numbers. And that's why I had to use the curly brackets and just list them out. But if it's every number between there, we use this notation. Because obviously I can't list every single number between -3 and 2. Any questions on this? Now, while I'm letting a few people write a little bit further, I will tell you there is a second way of showing a set of numbers that is not interval notation. It's called set builder notation. Your book does address it briefly. We used to spend a lot more time on it because interval notation has its limitations. As long as it's a set of all real numbers, we can use this. But if it's maybe only the counting numbers between -3 and 2, that would not actually be the correct notation. Set builder notation is kind of cumbersome. It looks like this. If I wanted just the counting numbers between -3 and -2, I would have to use this curly bracket x such that. So all x's such that they're between -3 and 2. So I would use this guy. But then I have to clarify what type of numbers I'm talking about. X exists in, and if I just want the counting numbers, in the integers, which was all those number sets that you guys have learned before, natural, whole, integer, irrational, all that. We're going to mostly focus on the real numbers, which means we get to use our interval notation. Every number between there, not just the counting numbers. But I want you to be aware there is another way of indicating these sets if they don't fall in the real numbers. So if you see that in your book, the set builder notation, that's the purpose of that, to kind of fill in the gap for things that are not all real numbers. Okay. We already used the words domain and range today, but not necessarily for describing a function or a graph here. I love this visual because I think it shows really nicely domain and range of this picture. Domain and range, although a very basic and very fundamental way of describing a set, is sometimes counterintuitive, and I'll show you. I think my second example here is exactly what I'm talking about as far as it can really mess with your head as far as what you want to say for the domain and range. But we will always write these in interval notation. So when I describe the domain of a set, it is describing the x values that that set can be. That means that its interval will be the farthest left a graph will go, comma, the farthest right a graph will go. Either parentheses or brackets. Our range will be the lowest a graph will go to the highest a graph will go. Again, either parentheses or brackets, whether it includes or does not include that value. I think one thing I forgot to mention that you guys were writing down in your notes on this last page, not included, anytime we use the infinity symbol, it goes on forever. Infinity is not actually a singular number. It cannot be included. So every infinity symbol will be parenthesed. Okay. Anyone still need this page? Now, for your notes-taking purposes, you can draw yourself some generic graphs here, but I will tell you I will post these later. So if you want like more perfect graphs and it's bothering you about your notes-taking, I always post these later as well. So domain is 100% focused on the x-axis. So as I go along my x-axis, finding out the farthest left the graph goes and the farthest right the graph goes, and I use those x values to describe it. Okay, so let's talk domain. As I look at this graph, it does just go from a dot to a dot. So the farthest, remember, domain goes farthest left, comma, farthest right. The farthest left that this graph goes looks like it starts here, yes? And now we have to decide, am I going to bracket or parentheses that? And the decision is, do I include that or not? What do you think? Parentheses. Open dot means I do not include. So if you did not know that, I'm going to mark it here. I picked parentheses because it was an open dot. I'll pick parentheses for 2 reasons. An open dot, it doesn't, well, actually 3 reasons. It doesn't actually quite get there, like approaching an asymptote, or it's heading to infinity. Comma, the farthest right. So I follow this graph, follow this graph, follow this graph, and then it stops here. And the farthest right this graph goes is 2. And again, parentheses or bracket. Bracket because it's a closed dot. Okay, now we start the same process with our range, but range uses our y-axis. Range to me is always the harder of these two because it does not necessarily read left to right. Now this one does, with me saying that. But it's so natural for us to read left to right, but a range does not have to read left to right. Domain reads left to right nicely, okay? So then I'm going along my y-axis and I find the lowest point that the graph starts, which would be here. So my range would start at 1. And I continue along my y-axis until my graph stops, which would be here, up to 2. Lowest point, comma, highest point. Again, I make the decision on parentheses or brackets based off of those dots. At 1, it was an open dot, which means we are not including that. So parentheses. Up at 2, closed dot. We are including that. Bracket. They do not have to match. I know that these both go parentheses, bracket, parentheses, bracket. That is not, they do not have to match that way. Okay? Questions? All right. Let's talk about arrows. Unless your arrow is very clearly perfectly horizontal or vertical, it will be continuing in 2 directions. What do I mean by that? This arrow will continue left forever and up forever. And when I say forever, I mean infinity. The left infinity is negative numbers, so negative infinity. The up infinity is positive numbers. Okay, so all arrows continue in 2 directions. Domain, we go on our x-axis. So what is the farthest left this graph will go? Negative infinity, right? Infinities we don't have to think anything about. They're automatically a parentheses. So it starts over here at negative infinity. I follow my graph along the x-axis until there is no more graph. It looks like our graph stops here along my x-axis, telling me the farthest right this graph goes, which is 4. I'm going to erase my mark here so you can see that that actually is a closed dot there. Closed dot, we already talked about, is going to be a parentheses. Bracket. Follow what I wrote, not what I said. Bracket. Okay, now the range, this is an example of where the range will bother you visually. Because again, I want to read my range from left to right, but we read, again, our range from bottom to top. So going from the bottom, our graph actually starts over here on the right, moving up my y-axis, right? The lowest point in our graph is actually way over here. Along my y-axis, that is a value of what? 0. So the lowest point in this graph is going to be 0, bracket or parentheses? Bracket, it does include that. But what is the highest point in this graph? Positive infinity because of this guy over here, right? It tells me that it is going to slowly continue up forever. And an infinity is automatically a parentheses. Questions? Okay. This is a little clip of what's called the greatest integer function. It's a step function. These can become challenging for domain and range. Let's talk domain first. Farthest left that this graph goes. So along my x-axis, we start seeing graph here at 1. Now, when it is a piecewise function, when there are breaks in our function, there is a potential break in either our domain or range. Okay? But as I go to, so it goes to 2 and stops, but the next, you see how the next graph picks up at 2? Which means our domain does not need to stop. If they overlap like that, the next piece picks up where the last one left off, we do not have to break in our domain. So it continues on to 3, where the next piece picks up and continues on to 4. There's our domain for this graph. It is a filled in dot at 1, so I would include it, but it is an open dot at 4, so I'd have parentheses it. And this is where this one gets a little challenging, and the vertical piece on this one I get is very different. Vertical, okay? So as I go up my y-axis, I start seeing graph at 1. Do I include 1? Yeah. Okay. But I don't have graph here, do I? So it like stopped at 1 also, didn't it? Because it doesn't overlap. I don't see graph again until I get up to 2. Agreed? Okay. So I actually only have 1. And then I have a little piece of graph starting at 2, but again, it doesn't go above 2, so it's just 2. You can use a union symbol or a parentheses or just write them next to each other. I really don't care on that, okay? And then we've got a last piece up here at 3. I use a union symbol to group them together. You do not need that. Parentheses, list them all out. Yeah. It would not. Because there's a line all the way across there, at some point you're including it. Yeah, that's a great question. He's saying if these were flipped, right? You're saying if that was the open dot was over here? Yeah. For our range, it would not impact it because at some point it actually will still equal 1. So we do still include it in the set. Other questions? Okay, we are going to stop there with our notes. We're not going to do our check for understandings today. Your assignment is on Google Classroom, but we are going to move on to our unit objective quiz, okay? For your unit objective quiz, and I can put your assignment up here too, it's not a big deal. I know that looks like a whole lot of problems, but again, they're real quick and like not like grouped together, so they're all listed individually. For your unit objective quiz, you are going to be able to use your calculator and your notes. Okay, you guys do get your notes for this. I do ask that you do your assessments in pencil. There is a tray right behind you. You just got yourself a new pencil. Keep it. I don't want it back. Okay, here's the weird thing about this quiz, which I'm afraid is going to throw people off here. There is one problem on the back. Do not forget to turn it over and do that, okay? So do these, turn it over, do the back, all right? There is a Form A and Form B, so I would not suggest trying to get help from your neighbor because then you'll get them all wrong for sure, unless they're really wrong and got the right answer for your form, which would be weird. And let's see, we're going to figure out where I'm going to set this up. Probably on that little podium right there, I'll have a little tent that says Form A and Form B, and you'll just put yours under whichever form it says at the top there. All right? Got it? We do have a little bit of extended time today because we've got TA also, but you have about 15 minutes left of this actual class before we transition into our TA time. When you are done, here's the deal. You turn in your quiz, you go back to your seat, you start working. I will give you the all clear when all quizzes are in, I promise, but you have to stay quiet until then, okay? Everyone deserves quiet time to work on their quiz. You cannot just start talking to your neighbor. So stay quiet until I say all quizzes are in. You may now work together, all right? Got it? Okay. So how am I going to do this? There's no pathway to walk in this room anymore. Now, if you choose not to take notes, you do not get to use your neighbor's notes for this. If you still do not have a graphing calculator, you are allowed to use that app on your Chromebook right now. Mm-hmm.